Okay, so now we're going to get into some of the mathematics of how to calculate what's going on with this interference. So the most confusing part is probably just all the variables we're going to be using and keeping everything straight. So we're going to go through the variables first. L is the distance to the screen, which is shown on the figure here. It's L. So the distance between the slits and the screen. The distance between the slits is D. That's right here. So the distance between the slits. Y is the distance from the center to whatever fringe we're talking about. Delta is going to be the difference in path length. We're going to go over that in a second here. M is the order number. We're going to also talk about that in a minute, but it's basically the number of the fringe we're talking about. Lambda is the wavelength. Now, notice I skipped over R. R is going to be the distance a wave travels, so the path length. So here on this figure, I have some nice looking waves, and we're going to just replace those with two vectors. So R1 and R2 to be able to figure out the path length difference. And so I'm going to switch that and kind of move it over and then put it on top so we can see that basically this is our delta, that's our path length difference. And now we have a nice right triangle in here that's also shown on this figure. Nice right triangle. And so delta is going to be equal to D is our hypotenuse on that triangle times the sine of theta. So that's where that equation has come from. Simple geometry. Okay, so we're also interested in the distance y. So how do we figure out what y is? Well, we use a triangle again, except now it's the triangle in the blue area. This is again a right triangle. And so we are going to say that we have the variable L as our distance and y. So since we have the two sides of the triangle, and presumably we can measure this angle, we're going to say that y is equal to L tangent of theta, which is very close to L sine of theta if we use a small angle approximation. So again, that is only if we have a small angle, and that's going to be typically under 15 degrees. So we will have some problems where that's appropriate and some where it's not, and I'll show you when you can tell the difference and which equations to use. So this assumes that L is much bigger than D, which is a valid assumption because L is typically on the order of a few meters, whereas D is a few millimeters. And that distance is much, much bigger than the wavelength. So where this is again in millimeters and the wavelength of light is in nanometers. So this is also using the small angle approximation. So these bright fringes, we established that delta is equal to d sine of theta, and that's going to equal to m lambda, where m is an integer. And this should make sense because delta is the path difference. This is just our measurements. And so the path difference, in order to have a bright fringe, has to be some integer multiple of our wavelength, and that integer can be 0 for our central bright fringe. The difference in path can be 0. They basically take the exact same amount of distance to get to someplace, or plus or minus 1, plus or minus 2, because we see these fringes going both to the right and to the left. So when m is 1, it's called the first order maximum. When n is plus or minus 2, it's called the second order. When n is plus or minus 3, it's called the third order. And when it's 0, it's called the 0th order maximum. So for the dark interference, it should be no surprise. Like we saw for sound, it got m plus a half lambda is equal to our path length difference. So m is again some integer. So in summary, for the bright fringes, we saw that delta is equal to d sine of theta, or m lambda. And we can also use the small angle approximation that we can get our distance to our bright is equal then also to lambda L d over m. So that's for the bright fringes. And basically just for the dark fringes, all we have to do is replace the m with an m plus a half in either equation. So it should come as no surprise. So the next thing we're going to do is see these equations in action. So we have a viewing screen separated from a double slit by 1.2 meters. So from the screen, that means that is that variable L. And so I have that indicated here. The distance between the two slits is 0.03 millimeters. That's D. Monochromatic light is directed towards the double slit and forms an interference pattern on the screen. The second order bright fringe, that means M is equal to 2, is 4.5 centimeters from the center. So from the center of the screen, so that's our Y value. So that's Y, and we would label it with a subscript 2. So the first thing we want to find is determine the wavelength of this particular light. So we go up to our equation with lambda in it. That's what we want to find, and rearrange that for lambda. So we get y d over ml. And we put all the numbers in, 0.045 meters. It's important to use meters in this format because we want everything to be able to cancel. 0.045 meters, 3 times 10 to the negative 5th meters. So we got meters squared right now in the numerator. Then I know m is equal to 2 because the problem tells me. So pay attention to the problem and it will tell you what m you are dealing with. So one of those meters cancel and I should have units of meters. So we get lambda here is equal to 5.625 times 10 to the negative 7th, which is same as 563 times 10 to the negative 9th meters, or 563 nanometers, which makes sense for light. Then it's asking us to calculate the distance now between adjacent bright fringes 1 and 2. So that's part B. So this is m is equal to 1 and m is equal to 2. So I'm looking for delta y, basically this distance right here. So that would be y2 minus y1. And if I substitute in those values, I get lambda L over d m2 minus lambda L over d m1. Notice I'm multiplying by the same thing, so I can pull that out of the equation. I'll pull it out here, lambda L over d m2 minus m1. And then we can put our numbers in. That's just 2 minus 1, so that's just 1. So really the formula reduces down to, for this case, lambda L over d. And so I can put those numbers in, 5.63 times 10 to the negative 7th times 1.2 meters, all over 3 times 10 to the negative 5th. And that'll give me a distance of 2.25 centimeters. And it's should be no surprise that it's half of the original value. Okay, now the next thing is for some examples that you will work on. Okay, so now we're going to do the same thing again, except for we're going to find the wavelengths of 2 different colors. And the Veritasium video that I mentioned also goes into this and actually shows you how we can get this rainbow effect on the edge if we're using the slits. So white light, so we start out with a non-monochromatic source, passes through 2 slits 0.05 millimeters apart, so that's D. And the screen is 2.5 meters away, so that's L. And then we get 2 distances for Y, either red or violet light. So 2 extremes for our spectrum. So we want to calculate delta. So lambda is equal to y d over ml. And so we're just going to put our 2 distances as 0.002 meters for our violet, 5 times 10 to the negative 4th meters, and 1, because presumably the problem doesn't say anything else about any other order number, so we're going to assume that this is the first time we're seeing this effect. And we get 400 nanometers for violet, which should make sense for violet. So we see here that we can do it with both different wavelengths, and it's so cool that we can measure. So the 2 millimeters versus 3.5 millimeters is something that you could measure with a ruler, and in fact you're measuring the wavelength of light with this simple calculation. Okay, so here's more of a conceptual question for you. So in the laboratory experiment, we produce a double slit interference pattern. And so we see that this is where m is equal to 0. And the point marked on the screen here is how much farther from the left slit than the right slit. So if lambda is the path difference to the fringe marked here is m equals 2. So the path length difference is simply 2 lambda to get to that second fringe. There it is, nicely typed up. And that's the end of this lesson. Next time we're going to move on to a single slit experiment.